Hey, today we'll finally meet one of the most important objects of study in homotopy theory, which is the category of spectra. We will develop many of its structural properties and study some examples. And furthermore, we will talk a little bit about the Posnikov Tower and how to think about spectra as a kind of derived category in a fancy way. I'm Achim Krause from Mathematics Münster. So we will write S star for the category of pointed spaces. So this is, of course, the slice category in the category of spaces under the point delta 0. And on this category of pointed spaces, well, we have a zero object, the point, and this gives us two very important functors, sigma and loops, suspension and loop space. Sigma and omega, suspension and loop space. These go from S star to S star, and they're defined via the following push out and pullback squares. So sigma x is just this push out, and loops x is kind of the dual pullback, where I write point instead of delta 0 now because maybe I like to think about these more as like spaces rather than simplicial sets, but I could maybe write delta 0 instead. And maybe if you're used to think about suspension and loops in a more geometric way, then it's a good exercise at this point to try and check for yourself that the functor sigma is left adjoint to the functor omega using this definition. Okay. So we can right away define what a spectrum is in terms of this. Namely, a spectrum is just given by a sequence of spaces, pointed spaces xi. So here I is given by non-negative integers. And together with equivalences from xi to loops of the next. So basically we're saying a spectrum is a space with a choice of infinitely many d-loopings, right? Think of x0 as the underlying space, and then x1 is a choice of d-looping, some space whose loop space is x0, and x2 is a further d-looping, and so on. So that's a nice kind of object, but of course we really want a category, right? So we need to define what maps are and so on. And we can surprisingly, one of the easiest ways to do this is to directly write down an infinity category. As follows, we let SP, the category of spectra, be given by the following infinite pullback of simplicial sets, where all these categories, EQ of S star, are simply the full subcategory of the category of arrows in S star on equivalences. So I consider just the subcategory of those arrows which are equivalences, but with arbitrary morphisms between them. This subcategory is, of course, equivalent to spaces as an infinity category. And then I need to give you maps in this direction from each of these factors to this copy of S star, and I need to give you maps in the other direction. So these maps are simply given by sending an arrow to its target, right? So if I have an arrow in here, I can just forget about everything except for the target object. That gives me an object in S star. And these arrows, these are given by omega after source. So those take an arrow, such an equivalence, to the loop space of its source. And so what do you get if you take this pullback? Well, a point, meaning an object in this pullback, an object in this category, meaning a point in this iterated pullback, will consist simply of a list of equivalence arrows like this, together with the condition that the target of one arrow agrees with loops of the domain of the next. So if we write that up, we see that objects are simply given by a list of equivalences like this, where we have performed the identification with the target of one arrow and loops of the source of the next. So we see objects are precisely spectra in this sense. And what are maps? So what are the mapping spaces? What do those look like? Well, a point in the mapping space from an object given by a sequence xi to the object given by yi. So informally, that consists of choices of maps or I shouldn't say informally, this is going to be actually a description of a point in the mapping space, but it doesn't describe, of course, the mapping space as a complete simplicial set. Right? I'm just telling you what a point is, and then informally the mapping space is going to be the space of such choices. So a map consists of a choice of maps from xi to yi for each I, and then these somehow need to be compatible with these equivalences, and we need to make this compatibility part of the data. So a map will consist of a choice of maps like this and chosen homotopies for each square like this. I'm indicating the homotopy by this arrow. And here you see why you really need to write this down as an infinity category. You could try to write down a one category where objects are spaces and equivalences like this, but then here you would run into problems, right? You can't compose homotopies in a strictly associative way. So yes, this is why it's surprisingly easier to write down the infinity category than, say, write SP as the homotopy coherent nerve of a certain simplically enriched one category or something like that. So now there's one more observation I want to make, which is that one can come up with an even simpler explanation or an even simpler description, which is simply that this infinity category SP, it's also equivalent to just taking the limit in cut infinity of the diagram indexed over non-negative integers, which has just a copy of pointed spaces everywhere and loops everywhere here. So if you're willing to input the infinity category cut infinity, then this is sort of an even slicker definition. It boils down to the same amount of data, right? A point in this limit is going to consist of a choice of objects everywhere here, and then choices of identifications between their image in the next one. And then the fact that you can write this also as this kind of pullback actually comes from the fact that limits like this over non-negative integers can be written in this kind of smaller way, where we just write down the objects and the one morphisms, and we don't have any data coming from the two morphisms in the non-negative integers. And kind of related to that, we can also give a different description of maps, which is one can describe the mapping spaces between spectra x and y as just a limit of the mapping spaces between the corresponding pointed spaces, and the map from 1 to, like from this for the index I to the index I minus 1 simply applies the loop functor and identifies loops xi with xi minus 1 and loops yi with yi minus 1. Okay, so what are examples of such objects? Well, if you start with any kind of space, it's surprisingly hard to deloop it. But you've certainly seen one if you've ever taken an algebraic topology course, which is the example where we have the spectrum called HA for any abelian group A, and here the ith space is given by KAI, the Eilenberg-MacLane space. This is a space with just the single homotopy group pi I given by A and all other homotopy groups given by 0. And here we have equivalences Ka I minus 1 to loops Ka I, because if you take loops of such an Eilenberg-MacLane space, what you're doing is you're shifting the homotopy groups down by 1 degree, and so this becomes a Ka I minus 1. And then the other important example, this is a little bit more subtle, is if you start with a pointed space X, then there's the so-called suspension spectrum, sigma infinity X, whose ith space is given by taking a co-limit over all k of loops k sigma k plus I x. So one way to think about this is if you just want a sequence of spaces with maps to loops of the next. Then since loops is adjoint to suspension, you could also start with a sequence of spaces with a map from sigma xi to xi plus 1. And one way to get that is you start just with a space and take all its suspensions, right? Each of these maps after suspension to the next one. But that's very far. So if you then adjoin over, you get that. The corresponding maps from the ith suspension of x to loops of the I plus first suspension of x are very far from being equivalences, of course, because loops and suspension are not inverse to each other, they're just adjoint. So here we're basically starting with that, and then we're enforcing loops to be an equivalence by simply taking this kind of co-limit where we add in more sigma and loops in every step. The maps in here are simply coming from the unit of the adjunction, right? There's a map from the identity functor to loops after sigma, and we're doing that somehow in between these summons, in between these two terms in every step. And it turns out if you take this co-limit, then this is a spectrum. And what goes into that? Well, if you loop this term, then you can pull the loop into the co-limit. This is due to the fact that loops was given as this pullback, and filtered co-limits commute with pullbacks in spaces. So you can pull the loops in, and then you see that you basically have just the corresponding co-limit. After re-indexing, you have the corresponding co-limit for the I minus first space. And so that makes this into a spectrum. And an important special case of this is the suspension spectrum of the zero sphere. This is so important that it has a blackboard bold letter, namely S, the sphere spectrum. So now one crucial fact out of these suspension spectra is that maps out of them behave in kind of a nice way. So if I take a spectrum Y and a pointed space X, I can look at maps between these spectra, and it turns out there's an equivalence between this mapping space in the category of spectra and this mapping space here in the category of pointed spaces, where I've passed to the zeroth space of my spectrum Y. And let me give you a proof sketch. So I'm going to produce, starting with a map from x to y0, somewhat canonically a map from sigma infinity x to y, and then claim that that defines this kind of equivalence between mapping spaces. So what's the idea here? Well, if I have a map from x to y0, then remember that y0 is also simply some iterated loops of the higher spaces in that spectrum. So let me just write this as loops k plus I of y k plus I. By the adjunction between loops and suspension, this is adjoint in the sense that this map under the adjunction gives me another map. It's adjoint to a map sigma k plus I x to y k plus I. And then if I loop this again k times, I apply omega k, I get a map from loops k sigma k plus I x to yi, right? Again, we've used that loops of yk plus I, that loops just, I can identify that with the lower space in my spectrum. And now here, I have now, for every k and I, produced a map like this. So in particular, for all k, I have a map like this. And those are compatible. This is why I wrote sketch here. Let me not try to check that explicitly for you. But these are somehow compatible under these maps that go into here. There's something going on with how we obtained these from the adjunction. And therefore, this gives me a map from the colimit over I, over k, loops k sigma k plus I x to yi. And this is just the ith space in the suspension spectrum. And now I'm going to point at this again, because now I claim that these maps from the ith space of the suspension spectrum to the ith space of y, those all fit together and define actually a map from sigma infinity plus x to y. And then if you have such a map, of course you can also restrict, right? I mean, we can recover out of that a map from x to y0 simply by looking at I equals 0 and restricting to the first term of my colim here. So the other way, going the other way is somehow easier. And everything we did here was so canonical that it turns out that gives you an equivalence. If one were to write this in a book and tries to make this super explicit, then the easiest way to do that probably involves a little bit of machinery where someone encodes the necessary stuff in larger diagrams. All right, so this looks an awful lot like an adjunction, right? It looks like an adjunction between the functor sigma infinity and the functor which takes y to its 0th space. And there's a very slick notation for that functor, which simultaneously works well with this adjunction and with the fact that we've somehow said that y is kind of an infinite choice of d-loopings of y0. Namely, the functor is, well, we define loops infinity of y simply as y0. So in terms of that, this lemma that we just proof sketched boils down to saying that the functor sigma infinity from pointed spaces to spectra is left adjoint to the functor omega infinity. This is kind of a nice version of the adjunction between sigma and loops, right? We just replaced somehow this by something else than pointed spaces, but this suggests that we can somehow think of this simultaneously as kind of infinite d-loopings and somehow also related to suspending a space infinitely often. We'll see today how these things fit together. So one little example for that, actually. Let me give you that after cleaning the board. So one nice example to see how this sigma infinity has something to do with suspending a space infinitely often. It turns out that for a finite pointed space, again, this means that it's, well, it comes from a finite simplicial set, or maybe a little more homotopy invariant. It's obtained as a finite colimit of copies of the point in spaces. we have that maps of spectra from my suspension spectrum of this finite space to the suspension spectrum of any pointed space are, by the adjunction given by maps of pointed spaces, k to loops infinity sigma infinity x. But now remember what this means. This is just the underlying space, the underlying zeroth space of the suspension spectrum. So we can just insert the definition of that. And I guess this is another nice perk of this notation, is that somehow it suddenly makes sense of this. And then here's where we use that k was finite. Namely, we can pull this colimit past k, right? K is finite, and so mapping out of it commutes with filtered colimits. In other words, we can write this as map from k into loops k sigma kx. And here we can again use the adjunction now between sigma to the k and omega to the k to write this as this term where I've suspended both sides k times. And of course, if you track down what the maps are in this diagram, from the fact that the maps in this diagram came from the co-unit of the adjunction, you can see that here the maps come from applying the functor sigma. So this is really somehow stable homotopy classes, or I guess, yeah, maps under stabilization. In particular, if you take pi 0, it would be something like stable homotopy classes of maps from k to x. So one particularly important example is that for k equal to the space S0, we see that pi n of the mapping space from S into sigma infinity x actually agrees with what's commonly called the nth stable homotopy group of x. And what that means is simply this kind of colimit, right? I can take maps out of Sn plus k into sigma k x, and then suspension gives me a map that increases the k, and I take the colimit over all of that. That's by definition what this pi ns of a space means. And we see here nicely that this is encoded into this suspension spectrum. Maybe at this point, since I haven't mentioned that yet, since spectra have these D-loopings built in, there's an Ekman-Hilton style argument that tells you that on homotopy classes of maps between two spectra, you actually have an abelian group structure. So this is not just applying to like pi n of the mapping space, but already to pi 0 of the mapping space, due to the fact that, well, you can, for example, you can write this as the limit over these maps from xi to yi, and then all of those have the yi be a double loop space. I mean, more than that, but in particular a double loop space. So all of these are abelian groups. So how well behaved is this category spectra actually? For example, how do limits and colimits look like? Right, we know that spaces have all kinds of limits and colimits. What about spectra? So the first and easy thing to notice here is that spectra has all limits, which means like small limits, filtered colimits, and a zero object. We'll see in a second that we have more than that, but these are the easy ones. So what's the idea? Well, first of all, a zero object is given by the spectrum, which just has xi given by the point for all I. Loops of the point is the point, and it's easy to check that, well, the mapping space into this and the mapping space out of this is contractible. So this is a zero object. What about limits and filtered colimits? Well, the point is that limits and filtered colimits commute with this loops functor. Right? For filtered colimits, we've already said that. That's because this is written as a pullback, and filtered colimits commute with pullbacks. For limits, it's just true in general that limits commute with limits. And so what does this tell us? Well, this means that if we have a spectrum, meaning a sequence of spaces together with equivalences from one to loops of the next, and we have a diagram of those things, then you can actually take the limit or the filtered colimit pointwise, right? You just replace each of these spaces by the corresponding limit, and this still forms a spectrum. You still get a map to loops of the next, and it's still an equivalence simply because loops commutes with limits. So this means that you can take these pointwise and then in fact, for example, from the formula for mapping spaces as just this limit of maps from xi to yi, one sees that the pointwise limit or the pointwise filtered colimit does actually still satisfy the universal property for limits or for filtered colimits. So all of these exist and all of them are simply formed pointwise. That's the crucial point here. So what about colimits? Well, we will need a little lemma for that, which is that the factor omega from spectra to spectra, right? That's still defined in the same way as on pointed spaces. I have a zero object, and so I can, for every object, form the pullback, where I form the pullback of the zero object with the zero object over my object x. So I can do that, and it turns out this is an equivalence. Contrary to what happens on spaces. So why is that? Well, thankfully, limits, in particular this omega, are just formed pointwise, so we can just see what it does. Omega takes a spectrum x0, x1, and so on. So of course, part of the data are also these equivalences from xi to loops xi plus 1, but let's keep these implicit. So this takes this spectrum to, well, loops x0 and then loops x1, loops x2, and so on. But loops x1 is just x0, and loops x2 is just x2. And so you can write this like this. the implicit claim being that these identifications are compatible, but it's not too hard to check. And what is this functor doing? Well, another way to think about it is that it just takes this whole sequence and it just re-indexes it. It just shifts it up, kind of. And, well, then I guess it doesn't have a zeroth space anymore. But the zeroth space is just determined by this data, right? Because every space is just loops of the next. So another way to think of this is you shift and then you fill in the gaps with loops. They're somehow determined. And of course, this has an inverse, right? The inverse is given by shifting in the other direction. Right, just forget the first one and shift everything back. And since the first one is always determined by the next one, it's just loops of that, these are inverse equivalences. So from that, it actually follows that, let me call this a proposition maybe. It follows that spectra has all colimits, and a good way to think about them is that push-out squares are the same as pullback squares and vice versa. So push-outs exist, and they're in this funny way kind of an inverse to taking pullbacks. And I'm not going to give you the details of the proof. It's surprisingly elementary, but kind of tricky. But the necessary ingredients are exactly what we have up here. So the claim is that an infinity category with finite limits, a zero object, and the property that omega is an equivalence actually has push-outs, and they are determined by the fact that push-out squares are the same as pullback squares. Maybe a little kind of moral justification for this is you can directly see that a special kind of push-out, namely the push-out that corresponds to suspension, that exists. Why? Well, we saw earlier that suspension is adjoint to omega. And if you know that omega is an equivalence, then suspension has no other choice than just being the inverse of omega. And the full proof, well, it's kind of a more involved version of that. The idea is that if you start with a square and forget its lower right corner, you can recover loops of the full square by taking certain pullbacks. But if loops is an equivalence, you can recover the full square. So pullback squares are determined by their upper right corner, and then you can check that that means that the lower right corner is a push-out. Well, not give you the details here. But of course, once we have push-outs, since we also have filtered colimits, we have all colimits. And let me note here that infinity categories with this property, that they have finite limits and finite colimits, and I guess a zero object, and push-out squares agree with pullback squares. Those are called stable. The claim is Spectra is such an example of a stable infinity category. It's kind of the most important one. But we've already seen other examples. For example, the derived category, the unbounded, like the full derived category of a ring, or of an abelian category more generally, also satisfies this. Essentially, for example, you can check directly that push-out squares and pullback squares are the same by their explicit formulas. Okay, so in our case, this now tells us that we do have colimits, but they're kind of computed in a funny way, right? These here were computed underlying. The colimits, the claim is that they're not computing underlying, because that's not even true for sigma, right? So note, sigma from spectra to spectra is inverse to omega. And since we saw that omega shifts the indexing in one direction, this means that sigma is this other functor that went unnamed here, that just shifts back. So sigma is simply a shift on the indexing. And you see that's very different from if we just pointwise took the suspension. Turns out that doesn't even give you a spectrum, because the maps to loops of the next space are not going to be equivalences anymore. So there is a more general formula for colimits here, which is you take the pointwise colimit, but then you again have to take this funny trick where you take like loops n, sigma n, and this kind of colimit to force it to be a spectrum anymore. There is this kind of formula, but it's not super useful. The more useful perspective is really to think about that you can get all your colimits from filtered colimits and from pushouts, and that you can kind of explicitly control pushouts by this stability condition. So here are two kind of nice things that we can say now. So one is that we can recover yi, the ith underlying space of y, as loops infinity sigma I y for any spectrum y. And why is that? Well, that's just because sigma just shifts, right? It shifts in the opposite direction to this. So if I apply sigma I get a new spectrum whose zeroth space is the ith space of y. That's why this works. And we can also give two nice examples now for homotopy classes of maps between the two different examples of spectra we have. So the first is maps from sigma infinity x into the n-fold suspension of such an Eilenberg-MacLane spectrum, HA, in Spectra. So this notation with the square brackets, it simply means homotopy classes of maps. So I could have written pi0 map as well. So what is this? Well, by the adjunction, I can also describe this as homotopy classes of maps from X into loops infinity of this. But that's just going to be the nth space of this spectrum. So this is the same as maps from X into KAN in the world of pointed spaces. And it turns out this is the usual relationship between Einberg-MacLane spaces and singular cohomology. This is the same as the nth cohomology of X with coefficients in A. And similarly, if you map out of the nth suspension of the sphere spectrum into any spectrum now, well, so I can write this as sigma infinity of S0. And what does sigma n do with that? Well, sigma infinity was a left adjoint, so it commutes with colimits. Sigma is a special kind of colimit. So I can also write this guy as sigma infinity of the nth suspension of S0. So I can write this as sigma infinity of Sn. And if you use the adjunction again, you see that this gives you maps from Sn into loops infinity y. It's now of pointed spaces. And so this is giving you the nth homotopy group of the underlying space loops infinity y of y. So you see that in this world, we can both recover cohomology of spaces, and we do get this funny homotopy groups of spectra as just homotopy groups of the underlying space. And the nice thing now, so in particular, if you plug in the suspension spectrum here, you're going to get some stable homotopy groups here, just to make that clear. But the nice thing now is, due to the fact that push-out squares and pullback squares are the same, if you map into something, then for both pullback squares and push-out squares in the domain, since they are the same, you're going to get some Mayer-Vietoris long exact sequences for this kind of cohomology. And similarly, if you map out of something into a push-out or pullback square of spectra, you're also going to get long exact sequences. So in particular, if you take push-outs and pullbacks against 0, so you get co-fiber sequences, there's no distinction between co-fiber sequences and fiber sequences here, as opposed to spaces. So for a co-fiber sequence, you're going to get long exact sequences both in this kind of homotopy and in this kind of cohomology. And that's why it's much easier typically to compute stuff with spectra rather than with spaces, because you can work with long exact sequences for everything, basically. Not like with spaces where you have a fiber sequence, but then thinking about the homology is super hard, or vice versa. All right, so we will now get to a more precise version of this statement, that somehow I can not only think about spectra as spaces with d-loopings, but also kind of as spaces suspended infinitely often. Of course, not every spectrum is a suspension spectrum, but it turns out that for every y in spectra, we have that y is equivalent to the colimit over I of sigma infinity of the underlying spaces and then shifted I degrees down. And maybe we haven't said so before, but due to the fact that omega and sigma are inverse functors, you can write things like this. And of course, this just means applying omega I times. But for some reason, it's customary to usually not use omega, to use the notation omega in spectra, but rather use like positive and negative powers of sigma, maybe because of the fact that topologists feel, at least in spaces, more comfortable with the idea of suspension than with taking loop spaces. But just think of this as shift, really, right? In spectra, we've seen both loops and sigma really just shift everything around, not very different from, for example, how it works in the derived category. So how does this go? Well, we'll see that somehow both of these guys have the same mapping spaces out of them. And then we'll apply co-unida. So let's take any spectrum Z and wonder about maps from Y to Z. Well, by the formula for mapping spaces, this is the same as maps in pointed spaces from Yi to Zi. But now, Zi itself is the zeroth space of a spectrum, right? Of a shifted copy of Z. So by the adjunction between omega infinity and sigma infinity, I can write this as lim of maps in spectra again, but now sigma infinity Yi, and then the ith shift of Z. And now, of course, since shifting is invertible, if I shift in the target, I'm going to get the same mapping space as if I shift everything back, right? So sigma minus I is an equivalence on this category. So I can equivalently write this as lim map sp sigma minus I sigma infinity Yi Z. And then, of course, I can pull this limit in, and I get map sp colim sigma minus I sigma infinite Y Z. Right, I guess I haven't said up here what the maps are, but of course the maps come somehow from the structure maps of my spectrum. Right, I have maps from Yi to omega Yi plus 1, these equivalences. These are adjoint to maps sigma Yi to Yi plus 1, which are not equivalences anymore, but I get maps like that. And then I can write down this map sigma minus I omega sigma, sorry. I have a map, right. I can write this as this thing where I put a sigma in here, right? This is due to the fact that sigma infinity commutes with colimits, in particular with sigma. I could pull this out and then I see that this becomes that. But now this guy maps to sigma minus I plus 1 sigma infinity Yi plus 1. Right, so these are the maps we use here. They also somehow come out of the structure maps and the adjunction. And that's all the ingredients we've used here as well. Right, we've somehow used the adjunction between loops infinity and sigma infinity. So maybe this is a little sketchy again, but the claim is that you get the same maps here. And now you just use co-unida, right? You have two objects of your category and maps into any other object are the same, are like naturally equivalent. That means they're equivalent. So this means that spectra are generated under colimits by suspension spectra. So you can kind of think of spectra as somehow a stabilization of spaces, but then we've also built in all colimits of these and these negative shifts. So now that we have that, we've seen somehow how we can make sense of homotopy of spectra by mapping out of the sphere spectrum, how we can make sense of cohomology of spectra by mapping into the Eilenberg-MacLane spectrum or shifts of the Eilenberg-MacLane spectrum. And now we might ask what sense can we make of homology? So we will see actually, once we talk about monoidal structures, that there is a formula for homology that's very similar to the cohomology formula. It also involves Eilenberg-MacLane spectra. But at this point, we can present a slightly different flavor of homology, which turns out to give the same groups. By the following construction. So turns out there's a functor from spectra to dz, which I'll refer to as homology, or maybe a little bit more precise, as singular chains of a spectrum, because you get a complex, not graded abelian groups, but you can, of course, then take the groups. And the idea is we take Y, let's call this homology or chains. The idea is we take Y to the colimit of the singular chains Let me write H for chains. I think I prefer that, right? Because chains is really like an actual chain complex, not an object in the derived category, and then you have to worry a little bit of how does the functor work and so on. I think I prefer writing H without a star for the object in the derived category, where we haven't taken the homology groups. So not to be confused with the Eilenberg-MacLane spectrum H. Maybe that's a little unfortunate. Anyways, so let me call that H. So HY is just going to be the complex I get from the object in here. I'm getting from the singular chains with Z coefficients of the space YI. And then I have this diagram here with this negative shift. So what I can do is I can just shift this down by I. And since this map here just involved somehow suspension, it turns out we still get a diagram here from the suspension isomorphism, right? We can pull that out to a shift. So this defines a functor, right? We've completely naturally associated to every spectrum this diagram, and then for every diagram we can apply the functor and take the colimit again. And so this functor somehow is characterized by preserving colimits and by taking sigma infinity x to h of x. So here we have somehow a different behavior as for homotopy, right? For homotopy, we saw that the homotopy of my spectrum is the homotopy of loops infinity of my spectrum. Whereas here we see that for suspension spectra, this doesn't give me the homology of the underlying space, which was loops infinity sigma infinity x, but of the space we started with. Right. And in particular, the sphere goes to the complex z in degree 0. All right. So, in some moral sense, maybe you should think of the same way as you think of this as being somehow complexes over the integers. You can maybe think of spectra as somehow complexes over the sphere, and this functor as some sort of base change. So let's try to make that analogy a little bit clearer. So we've had this notion of a suspension spectrum of a finite space appear before, right? Maps out of that were simply like a stabilization. So we now define the full subcategory of spectra on finite spectra as the full subcategory of spectra of the form sigma minus n sigma infinity k for k a finite space, finite pointed space. Right, so this simply includes all shifts of suspension spectra, of finite spectra. And so, for example, maps between them, once you like suspend the shift away, really correspond to the stabilization of maps between the spaces we started with. This is also sometimes called the Spanier-Whitehead category. It's really obtained from finite spaces by stabilizing. And maybe a good exercise at this point is to check that this is actually already closed under finite colimits and finite limits. And so one way to think about it is that it's somehow the subcategory of spectra generated by the sphere, by this guy, under finite limits and colimits. So what's the significance of this guy? Well, let me wipe the board and then I'll tell you. So it turns out that from this category of finite spectra, one can get a good handle on the entire category of spectra. So spectra is really ind of finite spectra. And we've seen the int category before in a talk by Thomas, where he explained to us that the int category is somehow universal, the universal thing I get from the category here by adjoining filtered colimits. And so the proof, well, we have a functor from here to here, coming from the fact that we have a functor from finite spectra to spectra, and we can extend using filtered colimits. So the universal property of int gives a functor, and then the objects from SP_fin in SP are compact, meaning mapping out of them commutes with filtered colimits. That really uses the adjunction, because map out of sigma minus n sigma infinity k of some colimit of some diagram of spectra. So let me maybe put the diagram index upstairs for this to not be confusing at this point with the fact that we also use lower subscripts for the underlying spaces. Then this is simply by putting the shift over here and then using the adjunction. This was maps in Spectra, but this is the same as maps in pointed spaces from K to loops infinity sigma n colim y yj, and then this is the same as maps from, and now you can commute the sigma n past colimits because it's a colimit. You can commute the omega past filtered colimits because filtered colimits of spectra were taken pointwise on the underlying spaces, meaning they commute with omega infinity. And then this is k colim y and then you can also commute the colim out here because K by assumption is a finite space. And mapping out of finite spaces commutes with filtered colimits. And then you add join back, and you've seen that you can commute this whole thing past filtered colimits. So they're compact in there, and that's the one thing you need to check. This category is fully faithful in here. And then the final thing you need to check is that somehow the functor is essentially surjective, right? And in the int category, objects are by construction filtered colimits of the objects coming from the generating category. So you have to check that every object in spectra is a filtered colimit of finite spectra. And the idea here is we write y as colim sigma minus I sigma infinity yi as before, and then each yi as filtered colimit of finite spaces, which is something you can always do, for example, by taking finite subcomplexes of your simplicial set and making Kahn complexes out of those. So with that in place, let me say a little bit more about the analogy that I just suggested, which is that this is a little bit like a kind of fancy derived category. What's the analogy here? Well, in the derived category of a ring R, we have the full subcategory perf R. And perf R is the full subcategory of perfect complexes. And perfect complexes are simply complexes which have a representative which consists of finitely many finitely generated projective R modules. So this is very analogous to this SP-fin, where this was like shifts of suspension spectra of finite spaces. And in particular, every object in SP-fin can be written as a finite colimit, as a shift of a finite colimit of copies of the sphere. So this is a little bit like a complex over, like a complex built from the sphere, from finitely many copies of the sphere, similar to how here things are built from finitely many projective modules. The difference is that we don't take free modules here, but it turns out that you can make sense of projective modules over here and don't get a difference. So, and similarly to what we showed here, it turns out that dr is actually just ind of perf R. So again, somehow this category of finite complexes recovers the whole thing. So we think of SP as, and let me put that in quotes, the derived category of this object S, which in particular I'm claiming here is some kind of ring. We'll see that later in a talk about symmetric monoidal structures. So as I said, everything in SP-fin can be built as a finite complex of copies of a sphere. It's a little bit like a chain complex, but there's some additional, of course this is not actually a derived category of a ring. The problem is that additional subtleties arise from the fact that, well, maps from S to S is not discrete. And so if you think about that, then it turns out there is a way to think about these objects in here as some kind of chain complexes. It's basically what a CW complex structure does for you. But this fact leads to the fact that this chain complex involves higher kinds of coherences. So, yes. But this is still a very fruitful perspective. For example, one can think about this functor h that we encountered earlier, dz, as base change along S to Z. So, as a last thing today, I want to talk about the Posnikov Tower in Spectra and how abelian groups show up as a full subcategory of spectra. Right? So here, this is, of course, this is in safe quotes, but still, I'm kind of suggesting here that the sphere spectrum maps to the integers. So what do I mean by that? Well, we've seen earlier that spectra have homotopy groups by mapping shifts of the sphere spectrum in there. So let's call a spectrum n-connective if pi I of x is 0 for I smaller n. And just for reference, this meant maps from sigma I of S into X. Homotopy classes of maps of spectra. And here I can be positive and negative, right? Because I have these negative shifts of the sphere floating around. And similarly, we call it n co-connective if pi I x is 0 for I bigger than n. And we denote by SP bigger or equal n and SP smaller equal n the full subcategories of n-connective or n-co-connective spectra. The subscript basically tells you in which degrees you can expect homotopy groups. So this looks a little bit again like what we did for the derived category, where we said we have like bigger or equal, like we have like a bounded derived category in there, non-negatively bounded or something like that. So it turns out there's again some kind of functorial way to truncate things. So the claim is that the inclusion of this category into spectra has a left adjoint tau smaller equal n. And the proof proceeds as follows. We start with x 0 given by x, and then we build spectra xi by the following process. We pick generators of pi I x I minus 1 and corresponding maps, or one corresponding map of the coproduct of spheres shifted to degree I into xi minus 1. So by construction, this is, since these were generators, this is a surjective map on pi I. Yeah, on pi I. And now we take the cofiber and now we take the cofiber of that map. So what does that mean? Well, we take, same thing cofiber always means, we take this push out, and that's going to be our xi. And we let, having performed this construction for all I, we let tau smaller equal nx be the colimit of all these xi. And what does that do for us? Well, actually three things. First of all, tau smaller equal nx lies in the n co-connective spectra. And let me maybe put the second thing I wanted to say in here. And what did I want to say here? Well, pi I for tau smaller equal nx is the same as pi I of x for all I smaller equal n. So what we're claiming here is this process kills all homotopy groups in degrees above n. Oh, sorry. Sorry, I mixed up the indices. I want to start with xn, and then the next one I'm going to build is xn plus 1, and there I kill pi n plus 1. So I start in degree n, I kill all the higher degrees, the homotopy groups. And why does that not mess up the lower degree homotopy groups? In particular, why does the second step not mess up what I achieved in the first step? Well, that's simply due to the fact that pi minus 1, or like pi I of s, is 0 for I smaller 0. For example, since this is a suspension spectrum. So it's something you can prove, that suspension spectra are always zero connective, or connective in this sense. I guess what really goes into that is somehow that if you take an n connective space and you suspend it, you get something n plus 1 connective. I guess you have to input something similar to Hurewicz there at some point. Okay, so these have no homotopy groups in degree smaller than I, And now I'm using this fact that somehow push-out squares and pullback squares are the same, so I get a long exact sequence for homotopy groups. And then you easily see that this changes homotopy groups in degrees bigger or equal I, but pi I becomes 0. Okay, and the other property is that every map x to y for a co-connective n co-connective spectrum y factors through all of these pushouts. And that's simply because here we're somehow adding cells of degree bigger than n, but these already map trivially to y because the higher homotopy groups of y are 0. So can kind of canonically extend over this push out in every degree and then over this co-limit here. So this means that every map like this factors canonically over tau smaller equal n, and this means that this is really an adjoint, like we promised. And now, definition, we let tau bigger or equal n be the fiber of the map from x to tau smaller equal n minus 1x. And now observe, since none of these steps changed the homotopy groups of x in degrees smaller equal n, but we killed all other ones, a very good intuitive way of thinking about this construction is that it simply eradicates all the higher degree homotopy groups of x, but leaves the rest unchanged. And from the fiber sequence here, we see that tau bigger equal n really just kills all homotopy groups of degree smaller n and leaves the rest unchanged. So we can kind of cut a spectrum apart into spectra with these homotopy groups, here in degrees smaller n and here in degrees bigger or equal n. And now the claim is that if we have an n-connective spectrum and an n-1 co-connective spectrum, then there's just no maps between the two. And as kind of a slightly less extreme case, the category which I get by looking at all the objects which are both n-connective and n-co-connective at the same time is equivalent to the one category of abelian groups. So here we're saying that between n-connective and n-co-connective things, the maps are actually not 0, but a discrete mapping space. Well, in the first case, or for the first statement, see that any map from x to y, since x is, or since y is n-1 co-connective, any such map factors through tau smaller equal n-1x to y. This is again using the fact that we have this adjunction. But now what is this guy? Well, it only had homotopy groups in degrees bigger or equal n to begin with. Now we've killed them. Now it has just all homotopy groups 0. And that means that all its underlying spaces have their homotopy groups being 0. but we know that in spaces that means that they're 0. So you can tell if a spectrum is 0 by knowing that all its homotopy groups are 0. And so this guy is 0, and that's all we needed to know, right? Every map just factors through 0, i.e. is the 0 map. For the other statement, we observe that pi n gives a functor and that mapping spaces are discrete. So for example, one can see the latter statement from the fact that pi I of the mapping space from x to y, where x is n-connective and y is n-co-connective, or I guess both are both, we see that this is the same as maps from sigma I x to y. And now this guy is, well, we shifted it up. So this guy is now more than n-connective. And by the first statement, this means that this is 0, because y is still n-co-connective. And so if you have a space, all of whose homotopy groups in higher degrees are 0, for I bigger 0. If you have a space whose higher homotopy groups are 0, typically that only tells you that the base point component is discrete and nothing about the other components. But we have this group structure on mapping spaces coming from the fact that Y is a loop space. So from that, one can see that actually all the components are discrete. Somehow all the connected components of these mapping spaces are homotopy equivalent. So this already tells you that it's a one category. How do we see that it's actually given by abelian groups? In other words, that that maps are precisely characterized by what they do on pi n. Well, if pi nx is free, then we can choose a map from a sum of copies of S shifted to degree n to X, which is an iso on pi n. Right? This is just what it means for pi n to be a free abelian group. I pick these generators, and then, I mean, the pi n of the sum is just going to be a sum of pi n of sigma ns, but pi 0 of s is really just z. So then this will be an iso, and thus it is an iso under tau smaller equal n, by which I mean that if I apply tau smaller equal n, suddenly it's an equivalence, right? This is just the fact that they have the same pi n and no lower homotopy groups. So we get an iso from, or an equivalence from map x to y to map sigma n s to y. Sorry, this is a sum. And this is then just a product of copies of pi ny whenever y is n co-connective. So in particular in this case. And if pi n of x is not free, we pick a surjection a map from this guy to X, which is surjective on pi n. And then the fiber has free pi n by the long exact sequence. And then we use what we just learned for maps out of this guy and maps out of the fiber, and we use the long exact sequence. So use the exact sequence for pi star of maps blank comma y, and from there this follows quite directly. So the takeaway here is we can truncate away homotopy groups, and if we have spectra with just a single homotopy group, then they're just characterized completely by that homotopy group, and the category of all spectra concentrated in a single degree like that is really equivalent to just the one category of abelian groups. So this is just the Eilenberg, all of these are just shifts of the Eilenberg-MacLane spectrum, and maps between them are precisely given by homomorphisms of abelian groups. And one way to think about what this tells us about all spectra is the so-called Posnikov Tower. So let me just give this as a little overview. So the idea is that for every x, have a tower of all these truncations of x, and x maps to all of them and is in fact the limit. That uses a little bit on homotopy groups of the limit of spectra, which I'm not going to discuss right now, but it turns out the limit of this, just you can check that it has the same homotopy groups as x and the map is an equivalence, so it's an equivalence. And all of these have homotopy groups, like the difference between any two, meaning the fiber here, just has a homotopy group in a single degree. What is that? Well, this map gets rid of pi n plus 1. So here the fiber is going to be an Eilenberg-MacLane space of pi n plus 1 of x shifted to degree n plus 1. And this is an incredibly useful tool because you can reduce many structural statements about spectra by first understanding them for Eilenberg-MacLane spaces like this and then working out how they commute with limits of a tower like this. But a little warning maybe, of course, this is very far, like just this data, just the homotopy groups, is very far from telling you how your spectrum looks like. So in general, there's some additional gluing data that goes into how to get from here to the next stage in the tower. And in principle, one can write down certain cohomology groups these live in. The idea is that this fiber sequence here, you can also shift this once by taking a cofiber of this. The cofiber of this map here is going to be just a further shift of this. And then the map here is going to be a kind of cohomology group of this spectrum. But of course, then you would need to inductively work out what these cohomology groups are. And so this is not very feasible in general, but for structural work, this is a very important tool. And in particular, we will see that some of the homological algebra that we did for just ordinary abelian groups and so on, can be understood by this viewpoint that somehow abelian groups live fully faithful in spectra. And then there's going to be ways to use the Posnikov Tower to reduce to these ordinary derived things from this fancier world of spectra. All right, that does it for today. Thank you for watching and hope to see you next time.